Section 9.5, and I called it more convergence, but I really should have called it convergence with series with numbers in them. Yesterday, when you learned the ratio test, that's what you should do first if you have a series with x's in it. And you should always do the ratio test first when your series has x's in it and you're testing for convergence. These tests that we're going to talk about are for series that have numbers in them only. And these are going to be some new convergence tests. Okay. So before I start, here are some tools that you have so far for series that have numbers in them. You have the nth term test, and this is the place that I like to start. The nth term test is a good place to start, but it only shows that your series diverges. A series can pass the nth term test, and we don't know at that point whether it converges or diverges. The nth term test means that you just look at your terms and you think of them as a sequence and you say, well, what does the nth term approach? If the nth term approaches 0, then you're in good shape. If it does not approach 0, then the series diverges. Okay, so the nth term test only shows divergence. So from there, I would go to the geometric series test. The geometric series test converges as long as your multiplier is between -1 and 1, and then it converges. And you even know that it converges to a over 1 minus r at that point. So geometric series, you can even say what it converges to. From there, we have the direct comparison test, and the direct comparison test means you have to find a larger series that converges or a smaller one that diverges. And if you can do that, then you have the answer to your question about whether your series converges. The problem with the direct comparison test is that we don't have a lot of series to use for direct comparison yet. You could use geometric series to compare it to. You could use the basic ones, the Maclaurin series that you know, so e to the x, sine of x, and cosine of x. Other than that, we don't really have a lot of direct comparisons yet. We will get more as we learn more tools, but that's the idea behind the direct comparison test. First, you have to have a series that you know something about. Okay, and then at the end of, yesterday you were working with the ratio test, and the ratio test says you take a ratio of your n plus 1 term divided by your nth term, and you take the limit as n goes to infinity. And if that limit is less than 1, then you're happy because you know that your series converges. If that limit is equal to 1, then you don't have an answer to your question, and that's when we're going to need these new tools. Okay, so that's kind of an overview of where we are right now. Okay, for the direct comparison test and the ratio test, remember that your series have to have positive terms, and we can make our series have positive terms by slapping absolute value bars around the terms. If we can show that the absolute value of our series converges, then we know that the series converges without those absolute value bars around the terms as well, because that's absolute convergence. Okay, so this is the new test. Your first new test today is called the integral test, and the integral test uses those improper integrals that you learned last chapter and says, well, I know that if I turned my sequence of terms, which are really just these values, right? If I turned that sequence into a function, a continuous function, then the area under the function, if I use whole number increments, the area would be an RRAM approximation of the integral. So this is the first term. This is how big the first term is because it has a width of 1. and a height that's equal to the function, so that would be the first term. And f of 2 would have this rectangle would have the area of the second term. So this area would be a sub 1, this area would be a sub 2, and if you add up all of those rectangles, you're going to get this series. Okay, so the integral test, if we can show that this integral converges, then we can show, that shows us that the series converges. Important though, it doesn't tell us what the series converges to, because this integral would be, as you can see, an over approximation of the series. The other thing is that it's important if you're going to use the integral test, because RAM would be an under approximation of that integral, it's important that you have a positive decreasing function, because you want to make sure that your integral is overestimating your series. So in words, the integral test is in your chapter, in your book. It's called Theorem 10. You're welcome to read it if you want to, but really what the integral test is saying is, first, turn your sequence into a function, and your function has to be continuous, positive, and decreasing. And then you check to see if that improper integral converges. If it does, then so does the series. If it does not, then neither does the series. So the integral test is kind of a powerful tool when you can use it. Here's an example of a series that you can test convergence for using the integral test. So pause, try it, and then I'll show you how to use the integral test on it. Come back after you've paused it. Okay, so we're going to create a function out of our sequence. So our function is equal to our a sub n. And then we are going to notice that f is positive for n greater than 1. And we're also going to check is f is decreasing for n greater than 1. And the way we would check that is we would check the derivative. So f prime of n would be, well, I'm going to rewrite this as n to the negative 3/2. So f prime of n would be negative 3/2 n to the negative 5/2, which is less than 0 for n greater than 1 because of this negative 3/2. So we just have to make sure that we have the hypothesis of the theorem, and we do. We've created a function that's positive and decreasing. And so then from there, we are going to check the integral from 1 to infinity of n to the negative 3/2, or f of n. Okay, so the antiderivative of n to the negative 3/2, we would add 1 to that. So actually we'd have to turn this into an improper integral, or it is an improper integral, so we have to turn it into a limit. And then we take the antiderivative, but it's still a limit. So that'd be n to the negative 1/2 divided by negative 1/2, evaluated from 1 to b. So if I do that evaluation, I have the limit as b approaches infinity of negative 2 over root b plus 2 over root 1, which is 2, because this goes to 0. So the integral goes to 2. Therefore, the integral converges. So the series converges by the integral test. It's important to note that you have to have a positive decreasing function, so you want to make sure you convince yourself that that's true. And so now we have another powerful tool for testing convergence. It's called the integral test. Okay, So what I'd like you to do is pause the video. I'm not actually going to do these on screen, so I'd like you to try the integral test for all of these functions given here and see if you can see a pattern. All of these series given here and see if you can see a pattern. So pause the video and try the integral test on them and see if you see a pattern. Okay. What I noticed when I did this is that this series converges. This one, when n is equal to 1, diverges. Sorry, not n, that exponent is equal to 1. When this exponent is equal to 0.5, I notice that it diverges. Remember the one that we did before was 1 over n to the 3/2, and that one converges. So if I'm going to summarize, what I would notice is that as long as this exponent here is bigger than 1, then we have a converging series. If the exponent is 1 or smaller, then we have a diverging series. So this brings up the next test, which is called the p-series test. The p-series test is exactly in that format, and if your exponent is bigger than 1, then your series converges. If your exponent is less than or equal to 1, then your series diverges. It's a quick proof for all of those that using the integral test that that's true, but these p-series tests, now you can just glance at a series and say, oh yeah, that converges or diverges. And then the other thing about p-series test is that gives us a whole slew of really good direct comparison tests. I shouldn't have said function here, I should have said series. So we now have a bunch of series that we know about convergence and divergence for, and we can use those for direct comparison. So to summarize where we are after part 1 of this video, we now have the integral test for convergence, and we have the p-series test for convergence or divergence. And so that's 2 more powerful tests for series, and notice that this series doesn't have any x's in it, it just has n's in it, and that was also true for our integral test series. The next video will have the final test for this unit.